Okay, that was easy. Here we go. That's about 5 minutes of great YouTube. So here we are. So bile acids and salts act as detergents. We talked about those. And we said they have amphipathic properties that allow them to act as an emulsifier and form micelles. We'll look at micelles in a second. They have emulsifying properties because of their hydrophobic and hydrophilic regions. And these are a couple reasons these are so important. So imagine what's happening is we've ingested lipids, and what's the most common dietary lipid? Triglycerides. So that's going to be the focus of this. The triglycerides go through the stomach into the small intestine. As they're going into the small intestine, they are combining with bile. So remember, those fats are essentially in an aqueous environment. And there's a diagram coming up that'll show this, right? So those lipids are going to be coalesced. They're going to be in droplets. By adding the bile, the fat's dispersed. That also allows the enzymatic process to be enhanced. So we're going to look at that. We'll talk about the major enzyme involved in triglyceride digestion and absorption in that whole process. Okay, so that's coming up. So let's look at micelles, and then we'll compare that to mixed micelles. So here's a micelle. You've talked about this in other classes, right? You talked about things like, okay, these are molecules that can make micelles. Remember critical micelle concentration? Okay, that's the amount of a detergent that's required to make micelles. I hope you talked about that, but you didn't. That's all right. But this is a micelle. It's not a lipid bilayer. Okay, so these are when bile acids and salts and phospholipids are the major molecules that make these micelles. And if you look at it, they're spherical structures that are crucial for fat absorption. So this would be, for example, this is probably a better diagram showing like phospholipids, the circle indicating the hydrophilic portion, and then the fatty acids that are hydrophobic kind of combine. So now you've got a molecule that has a hydrophobic core, but it's hydrophilic on the outside. So now what detergents can do is they can surround hydrophobic molecules, right? That's how laundry detergent works, how dishwashing soap works, right? They mix with hydrophobic molecules and they emulsify them. They put them in solution. That's what our gut does with triglycerides. So that's a micelle. This is what's called a mixed micelle. So these molecules up here, if you can see the structure here, this is actually taurocolate, each of these, right? So that's a conjugated primary bile acid. Here's the hydrophobic regions. Here's the sulfate group of taurine, and you can see this is formed a micelle. This micelle combines with this molecule. Basically, it mixes with it to form a mixed micelle. What's this molecule? It's fatty acid. This is a fatty acid. Here's a carboxylic acid end. Here's your methyl group. So that's a fatty acid. Hydrophobic. So it combines with the hydrophobic regions of the detergents, in this case, taurocolate. So now it's considered a mixed micelle because it's part bile acid, part hydrolysis product. So we'll look at that in a second. So that's what it looks like. Here's a diagram that shows a little bit more, a different way of looking at a mixed micelle. These diagrams on here show a bile acid or a bile salt mixing in with phospholipids to form a micelle, and because it's mixed with other products, we call it a mixed micelle. And here's some examples of common components of this. These are fatty acids of monoacylglycerol. We drew these before, right? So this is a hydrolysis product of triglycerides. That's what's in here. Now this, you would put in your notes if you want, not to scale, not drawn to scale. Because here's a mixed micelle, here's the enterocytes. Okay? The surface, here's the glycocalyx, right? Here's all the microvilli and the glycocalyx and all that. These mixed micelles can actually go in between these microvilli. So the mixed micelles interact with the surface of the enterocytes. So the mixed micelles interact with the surface of enterocytes. And that allows for the diffusion of their contents. That allows for the diffusion of their contents. So a key point there is the mixed micelles are not absorbed, just their contents. Uh-huh.
So when their contents are absorbed, where are they going straight into?
Into the enterocyte.
And then?
And then they're going to be, we'll go through all that. They're basically going to be reassembled and then put into chylomicrons. So far so good? So that's what that looks like. Now that's not the only things that are going to be in there. Anything else in the diet that could be in there? We talked about this when we talked about the absorption and transport of fat-soluble nutrients, or some other things that could be in there. About fat-soluble vitamins. Cholesterol could be part of this. So they would follow the same path. So let's look at this diagram. And I will, let's see, I think this one's good, this one's good. Oops. So maybe you want to title this diagram emulsification, digestion, absorption of dietary triglyceride. I think I might have figured out one of the issues here, sorry. I'm fully caffeinated, are you? Could be. That could be. We should do an experiment, huh? Liver, gallbladder, obviously. That's what your gallbladder looks like, a rectangle. That's why sometimes it has to be taken away if it looks like that. And I'm going to add in another one. This is, you probably don't even have to write this. That's the pancreas. Oops. Don't spell it wrong and then I spell it wrong. I'm just moving from pin to pin, whichever one works better. So this is the gallbladder. We're gonna say this is bile acids. We're gonna focus on that right now. So this is bile and bile acids. The pancreas is also gonna release some solutions. The lighting up here is shockingly bad. Here's our triglyceride droplets. Put a couple of these. And then over here we're going to have I'll get out of the way in 1 second. Smaller triglyceride droplets. And then over here we're going to have, these are mixed micelles. else am I missing? Here's our bile acid coming from the liver. Liver makes cholesterol, makes bile acids. They do this. Gallbladder releases secretions in, so does the pancreas. Do the same sphincter modi going into the duodenum. I have that here, yep. Okay, so let's start this process. This is triglyceride that's come in from the stomach. It's formed droplets because it's hydrophobic, so this is the oil and water thing. At this point, relatively large droplets. So in the first step here, we have emulsification. So we're going to just call this emulsification. I'll do this the best I can. Hopefully I'll be consistent. Bile and bile acids are interacting with the surface of these triglyceride droplets, and that's making them smaller. So I'm just putting bile acids here, some bile. Right, so these are emulsified. In other words, they become smaller. So now we have enhanced surface area. The pancreas also releases lipase. I don't know where I can put it. How about over here? We're going to call this pancreatic lipase. Converts triglycerides to monoacylglycerol and fatty acids. Pancreatic lipase is secreted at the same time bile is released into that small intestine. So over here, we're going to say that some lipase is starting to associate with these droplets. Okay, you can assume all of these are surrounded. You guys have good eyes in the back, hopefully. I'm just putting bile acid around these smaller triglyceride droplets. And now we have mixed micelles, which means these are a combination of bile acids and what? Hydrolysis products. So the mixed micelles have, we're going to say, monoacylglyceride and fatty acids. So what's happened here is this lipase that is now on the surface of these fat droplets is converting to monoacylglycerides and fatty acids, which mix in with bile acids to form mixed micelles. All right, this enzyme is taking triglyceride, creating product, putting it into solution, and now that is combining with the bile acids to make mixed micelles. Right, so these are essentially doing this. Now you have the mixed micelles. So here's the absorption vehicle, if you will. Because now what these do, mixed micelles, oh sorry, I'm going to erase. Not very nice. These do this. Monoacylglyceride, fatty acids, bile acids, making these mixed micelles that now allows the fatty acids and the monoacylglyceride to be absorbed. That's what we just looked at before, right? So now these hydrolysis products are being absorbed. This is a mixed micelle interacting with the surface of enterocytes. So these would be enterocytes. I don't know if you want to draw it like this and put some detail. Here's an enterocyte. Here's an enterocyte. That's what those mean. Okay? Contents are absorbed, bile acids are not. So bile acids do this. Bile acids stay in solution. Until the ileum. So I'm going to put ileum right here. So now that process has occurred throughout the small intestine, going from the duodenum to the jejunum, and now we're in the ileum. At that point, almost all the dietary triglycerides should be absorbed, but you should still have bile acids.
With the lipase.
What do you mean, what happens to it?
Yeah.
So we're here. So it's mostly associated with these triglyceride droplets. As they get smaller and this particle is hydrolyzed, the lipase is going to be in solution. The lipase is going to be in the same environment where there's proteases coming in from the pancreas, so it's degraded.
How do triglycerides get small?
You mean here to here?
Yeah, like I'm thinking of triglyceride as like one type of thing. Just kind of small.
No, there might be a, okay, triglycerides. Sorry, good point. So you might have 1,000 of them in here. And now it's like when you take the water and you put a detergent in there, you put oil on top, shake it up, it eventually separates again. If you have a detergent in there, the lipids stay in solution. They become smaller and soluble. That's what emulsification is. So now let's say we're going from 1,000 to 10 or whatever. Good point. Good? Now we're here. In the ileum, this is where it gets... You thought it was interesting so far? This is where it's really interesting. Say these are more cells. Very sophisticated drawing. In the ileum, this is what happens. This is a bile acid transporter. In the ileum, the bile acid transporter picks up the bile acids, transports them through ileal cells into this circulatory system. And in this case, they're going into, what circulatory system is this? Yes. Let me put it this way. Obviously, that's albumin. Now guess what circulatory system? Portal vein, that's the blood. So this is the portal vein. Remember our friend albumin made the liver, cycles through the blood, picks up some hydrophobic molecules, including bile acids. So what happens is that albumin helps the bile acids be transported to the liver. So albumin is a transporter of bile acids in the blood. If you say carrier on that one, I'm fine with that. So albumin carries the bile acids to the liver. And why is that happening? So they can be recycled. Do I have everything there? I think I do. Got that? So let's work off of this. Here's a little bit more detail on that. So this process is known as recirculation and excretion of bile, or referred to as enterohepatic circulation. And as its name implies, it involves the gut and the liver. If you measure the total bile acid pool in the body, it's something like 2.5 to 5 grams. It's a relatively large amount. It doesn't have to be bigger than that because our body reuses them. Now, what this shows is more than 90% of bile acids secreted into the duodenum are reabsorbed by active transport in the ileum. So this is an active transporter. So what are a couple of characteristics of an active transporter? Fast or slow? They're fast. Efficient? They're efficient. Are they specific? They're specific. They're binding specific molecules, transporting them using energy against a gradient if they need to. So it's a very efficient reabsorption process. And then they're bound to albumin, they go to the liver. In the liver, reconjugation to amino acids. And you could put, and rehydroxylation. Rehydroxylation, remember that? We said when these guys, primary bile acids, go into the gut, sometimes they're modified. One of the modifications can involve removal of a hydroxyl group. They become secondary bile acids. Some of those are reabsorbed and basically repaired. So they can be rehydroxylated. Yes, yeah, in the liver. I said reconjugation and rehydroxylation if necessary. And then resecreted. You didn't know this, but every time you eat fat, triglycerides, this happens. Your body stimulates the release of bile from the gallbladder, goes into the gut, helps triglyceride emulsification, digestion, absorption, recycles. If you followed one of these bile acids, it might do this 2 or 3 times during a meal. It's that fast. Okay? And that efficient. And this is another way of looking at it. I think I have mine backwards though. Yeah. But overall, same thing. Biles are released from the gallbladder. So is lipase. Okay. Bear with me. We're going to talk about how this is related to heart disease. Okay. Now, so you look at that process, would you say that dietary triglyceride absorption efficiency is high? It is. We're very good, fortunately or unfortunately, of digestion and absorbing triglyceride. It's probably 95 to 98% of dietary triglyceride is typically absorbed. And you can think about it in a perfect scenario when we need that energy, we're very efficient at absorbing a significant concentrated fuel source. Bad case scenario, like in mine, I'd be like, yeah, I don't really need more body fat. But overall, it's a good process because you can absorb significant amounts of it. Not everything is absorbed at that high of an efficiency. So if you look at cholesterol, for example, about 50% of dietary cholesterol is excreted. Right? So let's say you have 500 milligrams of cholesterol today. Only about half of that is going to be absorbed. The rest of it ends up in the feces. We don't absorb it. It's not an essential nutrient. Absorption efficiency relatively low. Probably the main reason, not an active transporter. So cholesterol is relying on just basic diffusion. It's not as effective as some of the other things. And I'll show you why that's important coming up. So years ago when they started associating dietary cholesterol with heart disease, and they realized, based on bile acid recycling, if we can increase the loss of cholesterol from the gut or the loss of bile acids from the gut, we can decrease blood cholesterol levels. So that's the rationale. In order to do that, they took advantage of this mechanism. They came up with a drug called cholestyramine. I don't know if you've ever heard of that. Have you ever heard of that? It's an older drug. They came up with better drugs now. But this is a powdered resin. People would ingest it. It's a medication. It goes into the gut. It binds bile acids. Decrease their reabsorption, increase their excretion. Therefore, new cholesterol must be used to synthesize the bile acids. So the net effect was reduce the risk of heart disease by reducing blood cholesterol levels. And here's the mechanism. This is why this is such an important pathway. Bile acid goes through here, comes from the liver, goes through the gallbladder, does this. This bile acid can basically be recycled. So the liver doesn't have to use a cholesterol molecule to make another bile acid. It's recycled. This cholesterol in the liver has lots of different options. The liver can make significant amounts of cholesterol. If the liver has adequate amounts of cholesterol in its cells, it'll export it. It'll secrete it. It'll put it into a molecule called a VLDL. It's in the same family as chylomicrons. So this VLDL molecule goes into the blood. Is converted to another molecule called LDL. That one you've heard of, right? And when we say LDL cholesterol, do we say it's good or bad? We say, it's bad cholesterol. Cholesterol is cholesterol. But it depends on where it is in the blood that determines whether or not it's considered good or bad. If it's part of LDL, we say, that's not good. We want low blood LDL cholesterol. What's the good cholesterol in the blood? HDL. We say, hey, we want high HDL, low LDL. And women, God love you, you have higher HDL than we do, than guys do. That's one of the reasons you probably live a little bit longer. It's a protective effect. Next quarter, we'll analyze your blood cholesterol in the lab. We'll separate it into different fractions, and we'll see what your total is, what your LDL is, what your HDL is, if you want to do that, okay? And that's why it's so important. Now, this LDL may increase cardiovascular disease risk. So what's one way of reducing this? Reduce the amount of cholesterol that's exported from the liver. So how can you do that? Partition more of this cholesterol going to bile acids rather than being secreted. So how does that work? Block this. I have CS as cholestyramine. So in your notes you can say, if cholestyramine is bound to bile acids, they're not reabsorbed. If cholestyramine is bound to bile acids, they are not reabsorbed. Cholestyramine. It's up there if you want to know how to spell it. Cholestyramine. Now, so think about what's happening here. So, if it's not reabsorbed, why is it not absorbed? You just told me a few minutes ago this transporter is specific. not just bile acid anymore. It's a bile acid cholestyramine combination. Blocks its absorption. So now what happens? Not absorbed. So look what happens to the bile acid, cholestyramine. Ends up in the feces. It's excreted. So now what happens here? Block this. We're not recycling. So what happens here? We're blocking this. The body will produce an adequate amount of bile acids in order to facilitate triglyceride absorption. So if you lose this, what do you think is going to happen to this cholesterol? Rather than going this way, it's going to become a bile acid. So in that case, what's happened is cholestyramine, this pen is now actually functioning as an eraser. If you lose that cholestyramine molecule, a new cholesterol has to be used to replace it. That's what this means. A new cholesterol molecule must be used to synthesize a new bile acid. So now this becomes more significant. This is reduced. Net effect can be decreased LDL cholesterol. Got it? Apply fiber. Remember last time what I said about fiber? Does it bind? Fiber works the same way. You consume dietary fiber on a consistent basis. Some of that fiber binds bile acids. And the same kind of process occurs. So dietary fiber can reduce blood cholesterol, including LDL cholesterol.
Would you say that fiber is less efficient than cholestyramine?
Yeah. But they don't use cholestyramine that much anymore. And the reason they don't is they came up with another class of drugs called the statins. Have you ever heard of those? So the statins include Lipitor, Crestor, and a few other trade names. They don't work by this mechanism. Statins decrease this. Statins decrease cholesterol synthesis, period. And so what that does is that decreases secretion, but they can do it to such a high level, they also increase uptake of cholesterol from the blood into the liver. Now we'll talk about those in 329 lab. I'll tell you how those work after we do your blood lipids. But they're a drug, so ideally people are not on them. They use other means to stay off them, but statins are one of the most, I'll say, successful drugs in pharmaceutical history. Millions and millions of people are on them.
If someone's on statins but then eats a really high cholesterol diet, could they gain higher cholesterol than if they weren't on them?
Probably hard to do. Yeah, we tend to make more cholesterol than we consume from the diet. Yeah, I mean, yeah, probably not. Yeah.
So did you say fiber was doing the same, it was creating the same process that cholesterol was?
That cholestyramine is, yeah, it kind of, yeah, so it increases bile acid excretion.
Okay.
Yeah. That's one of the ways fiber works. Good there? Okay. Now let's go through and talk about, so that was gallbladder, some on the liver. Let's talk about the pancreas now. We know the pancreas makes digestive enzymes. It makes bicarbonate. And what does bicarbonate do? Affects the pH. Increases or decreases? Yeah, we say it neutralizes because it tends to increase the pH, yeah. I'll draw a reaction in a second on the board. Actually, let me draw it right now. So this is bicarbonate. So here's our proton. Combines with bicarbonate to form carbonic acid, which is here. So this is bicarb. So the pancreas releases bicarbonate into the small intestine. And so it neutralizes those protons from the stomach. So that's one of the ways our body controls the pH of the duodenum. So you want to remember this reaction. Right? pH is a function of protons. These protons are no longer free in solution. They become part of this molecule. So pH goes up. Becomes more neutral. Right? And the pancreas also makes hormones. We've talked about insulin. We know what insulin does. We know how it works. The other hormone we might have mentioned is glucagon. Glucagon is also coming from the pancreas. Glucagon, though, is from a different cell type. Glucagon is from alpha cells. Secrete glucagon. What does glucagon do to blood glucose? Increases it. So it is kind of the opposite of insulin in that regard. So the pancreas is doing both increasing and decreasing blood glucose depending on the blood glucose concentration the pancreas is exposed to, release either insulin or glucagon. So that typically is going on 24/7, that balance. And we'll talk about how it does that coming up. Here's how important those digestive enzymes are. The digestive enzymes from the pancreas are responsible for digestion of, so you say pancreatic enzymes are responsible for the digestion of 50% of all ingested carbohydrate. 50% of all ingested carbohydrate. 50% of all ingested protein. 90% of dietary fat. And that's because of that pancreatic lipase. So that's one of the most important functions of the pancreas, is the secretion of important enzymes. Pancreas is made of two main cell types, exocrine cells, endocrine cells. What does endocrine imply? Hormones. And exocrine are just secretory cells. So we'll talk about those, sometimes referred to as acinar cells. This is kind of an overview of the pancreatic structure. It's an interesting tissue. If you remove it from an animal, it looks like a little piece of fat, but you can see the vascularity to it, and it's kind of a pinkish color. It's not dense at all. It immediately floats to the surface of your buffer or whatever you have. And you look at it and you're like, wow, it looks like a piece of fat. Extremely important tissue, obviously, with specialized function. Overall, though, if you look at the kind of the types of cells in the pancreas, about 80% of the volume of the pancreas are exocrine cells. About 80% of pancreatic volume is exocrine cells. About 2% endocrine cells. And so if you've done the big math, about 18% is mostly structural cells. So one of the things that should indicate is the small portion of the pancreas does an extremely important function, an endocrine function, by releasing insulin and glucagon. So any problems with those cells or anything that's happening in those endocrine cells can be problematic, especially with insulin. Okay? So the exocrine cells are releasing, so this is showing acinar cells that form these structures. So when these acinar cells are excreting substances, they kind of work out this gland into what would you say, like a secretion system of the pancreas that now dumps it into the small intestine, the duodenum. So they're making, here's bicarbonate, or this is sodium bicarbonate, same thing. Digestive enzymes are coming out of those acinar cells. And then the endocrine cells, they're not putting substances into the gut. Where are they putting their substances? Into the blood. So glucagon and insulin are released into the blood, and they affect distant tissues. Okay, I think I went through most of this. The proteases are mostly secreted zymogens. What does that bring to mind? Pepsinogen in the stomach, right? Pepsinogen and pepsin. So we'll talk about, when we talk about protein digestion, we'll talk a lot about the proteases and how they function in this process. For right now, really basic. Your textbook goes through a lot of these enzymes and secreted molecules. Don't worry about all those. They have a big table in there. Don't worry about those at this point. Questions so far? That's probably a good place to take a break. So stop right there. Then we'll just finish up the hormones. That'll probably take about 10 or 15 minutes, and we'll start carbohydrates.